In this recording, we will solve a couple of problems to compare the difference of means and see whether the difference is statistically different or not. Let's get going. Let's look at the first problem. Here we are looking at a group of patients who had heart attack. And we want to compare the two different types of treatment. One is the conventional treatment, which we call as the control group, and the other is the embryonic cell stem cells treatment, which is the treatment of our interest. And we want to see whether the patients who had heart attack, when they were administered each of these treatment, did the change in the heart pumping rate because of this new treatment different, statistically different from the control group treatment. So we have the table here. So we have 9 patients in each of the groups. We have the change in the heart pumping rate for the ESC treatment and the control group. And we have the associated standard deviation and our variance also specified here. Our null hypothesis is whether you take the conventional treatment or the ESC treatment, it does not make a difference. And we want to test, our claim is that ESC treatment helps improve the heart functioning following a heart attack. So before we apply the test, we need to verify whether the data set meets the preconditions. So the test of independence, each patient is randomly assigned. So we can see that each patient is randomly assigned. And the test of normality is primarily to see if there are any extreme values in the data set. Even if the data set is not very very well distributed normally, the tests are sufficiently robust as long as there are no extreme outliers. So we have both these conditions met. So we can apply the t-test. So let's compute the t-statistic for this data set. First thing is the point estimate. So the point estimate is the difference between the change in heart pumping rate for both the groups is equal to x bar for ESC minus x bar for control group. So that's the difference. And we want to test whether this 7.83 is significantly different from the 0 or not. Let's compute the standard error. Standard error is simple, equal to square root of S1 square by N1 plus S2 square by N2. And that turns out to be 1.94. Right? And since we don't have the sigma available for the data set, we will approximate sample standard deviation in place of sigma. Let's compute the degrees of freedom. Many of the researchers use the minimum of N1 and N1 minus 1 and N2 minus 1 to compute the degrees of freedom. But the more appropriate formula when you have significant difference in the sample variances and the sample sizes. So here we see that the sample variances are significantly different. So we will use the Welch's formula for computing the degrees of freedom. So so the degrees of freedom is, let's kind of put the numerator divide by denominator. So in the numerator, we are looking for S1 square divided by N1 plus S2 square divided by N2. Let's come to the denominator. So in denominator, we have S1 to the power 4, S1 to the power 4 divided by, let's put the denominator in another bracket. So that's N1 square divided by, multiplied by n1 minus 1. All right. And let's take this term and calculate the second term of this, plus power 4. So in that case, we will use I6 to the power 4, that's S1 power 4, and S2 power 4 divided by, let's put the whole denominator in the bracket. We want n2 square multiplied by n2 minus 1. Enter, and we see we get the degrees of freedom 12.22. So we approximate it to 12, and we can calculate the t statistic. So the t statistic is simple. We want to calculate the difference divided by standard error, right? And that comes out to be 4.008. And we will test for t and with the associated p-value with this distribution for a two-tailed distribution will be, we need to specify our p-value, comma, the degrees of freedom, right? And we see that the p-value turns out to be 0.002. Right? And this is, so p-value is lower than 0.05, that significance level. Therefore, the difference is significant. Since the difference is significant, we can say that our inference is, our decision is, there is enough evidence to support the claim that the ESC meant heart pumping rate. Right? So let's look at another problem where we'll even calculate the descriptive statistics from scratch. So this pertains to a data set of North Carolina birth statistics. And what it says is there are two variables. Primarily, first variable is whether the women in the test group smoke or not. And the other variable of interest is the birth weight in grams of the newborn child. We want to test whether the smoking habit affects the birth weights of the newborn at 0.05 significance level. So we are saying that our null hypothesis is that the difference of the birth weight for the child born to a smoker versus non-smoker is same, and there is no difference. And we are saying that smoking habit affects the birth weight. So we want to test whether the non-smoker women give birth to heavier child or a less heavier child or not. So the data set is here. So our interest data set is the smoke variable and the birth weight in grams variable. It's generally a good strategy to create a copy and work in that so that the original data set is never affected. Working, and we can remove the variables which are not of our interest. Right, so we have got the only two variables which are of our interest. So first thing is, how do we calculate the basic statistics? So for that, we will use the pivot tables, and we would like to keep it in the working sheet here, and let's apply. So we bring smoking habits, birth weight in grams. So we want average. And then we want to restrict it to 2 decimal places. We want to next compute the count of this. So we can go for count, and we just call it as n, and we don't want any significance digits. That's how we get the n. And I can rearrange the order. Then I want to calculate the standard deviation. So I once again bring it to this and calculate where is my standard deviation. And we want to make it to 4 decimal places. But in fact, 2 decimal places should suffice. So this is how we have generated the statistics, which we can use in our data set to perform the T analysis. So I can simply copy, take it here, and paste. All right. And of course, we can calculate the variance. So before we apply the test, we want to check whether it meets the test of independence and the test of normality or not. So let's do the test of independence. So we don't have any information here whether these women are selected randomly or not, but we can assume that these have been collected for all the women who came to the North Carolina hospital where these women came for childbirth. And we see that the data is not selectively reported. So we will assume that sample are simply drawn. Now for the test of normality, there are more stringent tests available, but in our case, what we will do is we will use the visual inspection of it and see whether the data is normally distributed or not. So for that, what we need is we need to separate the birth weights of smokers and the non-smokers. Smokers. So how do you extract it? So we know that the 0 is the case of non-smokers, that's 1176 values. So that's 1176, command shift up, and we get all the values of the non-smokers. Similarly, we can extract all the smokers values, which is indicated by 1. So we select the smokers, and we put their birth weights here. Now what we can do is we can simply create a basic histogram based on each of these. So we go to the top, insert histogram, and we get to see the histogram of our title. Let's make it center overlay. So non-smokers. I can simply copy, paste it underneath one more time, and just reassign the data set to smokers. Select the data and say that we only want to go up to for the 200 values. Column J. J201. Let me delete and recreate this. Insert histogram, and this is the one for smokers. So we see that the data is reasonably normal and we don't see any issues in terms of outliers. We can also do the box plots to check if there are any outliers. And let's change the data so that only this is considered and the horizontal labels are drawn from here. Right. And we see that the smokers, non-smokers, 0, smokers, 1. So we see that the non-smokers non-smokers tend to have the child born to non-smoking women tend to have a higher weight than the women who smoke. And we see there are just 1, 2, 3, 4, and 1 outlier. So in a data set of 1176, just 4 outliers, and in a data set of 200, just 1 outlier. So there are no outliers, and data is distributed. All right, so let's get going with our calculations. So the first calculation that we're going to do is, in fact, what I can do is I can simply copy this entire bunch of cells, and let me ensure that it's from H15. So I just use H15, and all the formulas work exactly the way they worked in the previous sheet. So we don't have to enter the formulas again. And this is the specialty of templatizing. If we keep the structure same, the data set can be replaced and we get to use the formulas. So the difference between the weight of the child born, or the newborn child, is 227 grams. Standard error is 38. Degrees of freedom is 276.9. And the t-statistic is 5.864. The corresponding p-value is 0.000. So it's significant, fairly significant. So the inference is p-value is lower than 0.05. Therefore, it is significant. So there is enough evidence smoking behavior affected the weight of newborns. Let's look at another question now, exams. So an instructor decided to run 2 slight variations of the same exam. Prior to passing out the exams, she shuffled the exams together to ensure that each student received a random version. Summary statistics for how students performed on these 2 exams is shown in the table below. Anticipating complaints from students who took version B, she would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult than the version A. So there are 2 versions of papers. The instructor wants to just confirm whether each of these versions were sufficiently similar or not. So we use the student performance as the basis for comparing these versions. So instructor wants to ensure that both the versions of the paper are same. So essentially, if at all you see any difference in the performance score, we want that to be 0. If there is a difference in that case, we will infer that the version A and B were not same. So we will perform the preconditions. So students received random version of the paper, of the exam paper. So first condition is met. Now for the test of normality, we don't have enough data on it. So, but we will also assume that she did not selectively report the data, and all the students were in the same class, and we can assume it to be normally distributed. So you can use the t-statistics, t-distribution for this. So again, we can pick up the formulas from here at 15, okay. And I paste it, everything gets computed automatically. So we notice the observed difference or the point estimate of the difference of means is 5.30 with a standard error of 4.60. And we will use S because we don't have the sigma. And the degrees of freedom, which we have calculated using this formula, is 45.97. And the t statistic is 5.3 divided by 4.620. And that happens to be 1.147. So the t statistic is having an associated p-value of 0.257. So p-value is higher than 0.05. Therefore, difference in the scores is significant, is not significant. So therefore, there is no evidence in the observations or there is enough evidence in the observed score to not reject the thesis, that is version A and version B are similar. Right. So that's how we perform the analysis. So after this, we will look at a more than two variables simultaneously in our computations through ANOVA.